So we are going to continue on our topic on approximation algorithms. Last time we looked at the traveling salesman problem. So let me refresh your memory a little bit on that problem. So traveling salesman problem, TSP, what you are given is a complete weighted and unidirectional graph. G. Okay, so this is a given. Such a graph as input, and what we want to know, or what we want to find, is a cycle a cycle that goes through all the nodes exactly once, except the starting node and the ending node, because that's the same node. Exactly once with the smallest total weight. Okay, so that's TSP. All right, then we know that if the cost or weight, okay, so we also call that a cost function. So if the cost function C is satisfying the triangle inequality, so if C satisfies the triangle inequality, then we have an approximation with a ratio 2. Okay, so the algorithm is to start with a minimum spanning tree, and then you do a pre-order traversal, and in it, all the nodes in this tree, in this pre-order traversal, will form a cycle, and that's the cost of that cycle, or the total weight of that cycle, is bounded above by 2 times the minimum cost cycle. So that is the idea. So that means that the triangle inequality plays an important role. So then we wonder if the cost function does not satisfy the triangle inequality. For instance, for airline ticket, so you think about the price of an airline ticket is the cost function, then a direct flight sometimes is cheaper sorry, a direct flight is more expensive, not cheaper, more expensive than you going through other stops, right? So let's say so this is a direct flight, but then you have also another way to do is to go here first and then go there. So the airfare by going this route would be normally cheaper than direct flight. So then for such a cost function, it does not satisfy the triangle inequality. So as you can see here, even we want to find an approximation algorithm to find a cheapest airfare to do a cycle tour, starting from one city, going through every other city exactly once and coming back. So that's still we're going to show that for this problem we don't have approximation algorithm in polynomial time with any constant with approximation ratio of a constant. So that's we put things into the real life. That's what it is, right? So suppose you are given money and you, well, not a lot of money, but certain amount of money, and you are asked to find a way to go through every other city exactly once, starting from Boston, going through all, let's say, all the major cities in the world. You can define the major cities and coming back to Boston, but you can only go through each city exactly once. And you want to find the cheapest airfare to do so. So we know in general, this problem is NP hard. And then we try to find a approximation algorithm. And we know that if this airfare satisfies triangle inequality, we know that we have this approximation with a ratio 2. Now, if it does not satisfy triangle inequality, which we know that airfare doesn't satisfy triangle inequality, we don't even have a way to find an efficient, such a tour efficiently with an approximation ratio of any constant. Okay, so that's what we're gonna show today. So let's now move to that slide. So let me remove this. Okay, so now let's look at this theorem. Suppose that the cost function C doesn't satisfy the triangle inequality. And if P is not equal to NP, then for any constant R greater than or equal to 1, there is no polynomial time approximation algorithm with approximation ratio R for TSP. Of course, this assumption is a reasonable assumption because if P is equal to NP, then of course, traveling salesman problem can be solved in polynomial time. Well, that's even the optimal solution. Okay, so if P is not equal to NP, then we don't have approximation ratio for any constant. So how do we do this? So actually the construction is pretty straightforward. So now let me open up a whiteboard here. So let's say we want to show if TSP, so let's say if TSP without triangle inequality or dissatisfying triangle inequality. Okay, so let me change that word here. if TSP dissatisfies triangle inequality, then we are, and it's solvable in polynomial time. And is, or and well, what I mean by solvable means that it has approximation ratio, algorithm is a ratio R for any constant R. So let me write that one down here. And has an approximation, which is a polynomial time. So which is a pretty p time, which has a polynomial time approximation with ratio R for any constant R greater than or equal to 1, then we can solve the Hamiltonian circuit or Hamiltonian cycle problem in polynomial time. And this problem is NP complete. Okay, so then that implies that P is equal to NP. And that violates to our assumption. So that means now we are going to, so because we try to solve this problem, Hamiltonian cycle problem, use TSP, okay, use this assumption. So that means now we're, so given, so Hamiltonian cycle problem means that you are given a undirected graph, you want to know whether there is a Hamiltonian cycle, which means that that connects all the nodes exactly once. Okay, and that's a cycle, and that forms a cycle. So given G, I want to make connection to TSP. So that means that we need a complete graph and also we need a cost. So given G, we construct G prime. So this will be weighted and complete. Okay. So so is it complete? That means that we will, so this G prime has an edge for every pair of nodes. So now we just need to define a cost function. So this will be UV. So for any UV on the graph, we define this cost function here. So we will set it to 1 if this edge is in E. So let's call this VE. So if an edge is in the original graph that we are given, we'll set the weight to 1. So in other words, we set the cost to 1. Otherwise, that means that we add, so G primes are complete. So that means that if it's not in the original, if an edge is not an original, we will, so that's a newly added edge, then we will set a cost that will be much bigger than what it was, then much bigger. So in other words, you assume that I have, let's say, a Hamiltonian, if there is a Hamiltonian cycle in the original graph, then its weight is just, I'm sorry, its weight, because we set it to 1, its weight is just G. I'm sorry, the size of V, not G, because all of them is V. It's in the original. Right. So then we know that we can approximate this within a constant bound of R. So that means that if an edge is not in the original, not in G that we are given, we're going to set that weight that's much larger. So that will be, let's say, R V plus 1. So it's larger than 1. So in other words, as long as one of these edge is included in your solution, then I know that I don't have an Hamiltonian cycle in G. Okay. So now we have this, and then now, so now we have a TSP, we know that this does not satisfy, doesn't satisfy triangle inequality. Okay, so IEQ, so let me just use IEQ for inequality. Okay, so it doesn't satisfy because if you have an edge that's not in, say, let's say this edge is in E, this edge is in E, but this is not, so that is RV plus 1. So of course, you know that this edge is not smaller than the weight of these, the summation of the weight of these two edges. So it does not satisfy triangle inequality. Okay, so now because of this problem, if I have an approximation ratio of R, so that's what it is, and then you compute, so you want to use this approximation algorithm that returns a tour, right? A tour or a cycle with minimal cost. Okay, so that minimum cost is with a ratio R. So now we know that if the original graph G, has a Hamiltonian cycle, then on this weights, the algorithm, the approximation algorithm on G prime will return the original Hamiltonian cycle with a weight at most R times V, because we know that the R is the approximation ratio, the original cycle, all of them, you add them up, you have this many edges. So the weight, the total weight is just the size of the nodes. So then I can, if I have a cycle, then I use this TSP algorithm, then I look at the results, then I know there is a Hamiltonian cycle in the original graph. Otherwise, if the TSP algorithm returns a cycle with total weight greater than this, that means that one of these edge has to be used okay, has to be used. That means that the original graph does not have a Hamiltonian cycle. So then we solve this Hamiltonian cycle problem in polynomial time. Okay, so that's the proof.
So, Professor, a quick question here.
Yeah.
With the ratio r, it says for any constant r greater than or equal to 1, shouldn't that be greater than 2? Because if we are using approximation,
Well, so in other words, approximation ratio could be greater than or equal to 1, right? We just don't, the lower bound, you cannot be smaller than 1, but it could be 1. When it's 1, then it's optimal. So that's still possible. We just don't know. So you're saying that if r is equal to 1, then, well, let's say just r greater than 1. How's that? Instead of greater than or equal to 1. Let's say just r greater than 1. Because we know p is not equal to np, so it cannot be 1. So get rid of this equal. Just greater than 1. Okay. Would that answer your question? Hello? What? So you're saying r is equal to 2, but so why do you say r is equal to 2? Hello? Hello?
I think her mic is really quiet. I can hear her speaking like really softly off somewhere.
Ah, okay. So maybe, so yeah, we should get rid of that equal, because when r is equal to 1, that means that we solve.
Sorry, can you hear me now?
Oh yeah, I can. Yeah.
So I think it's my understanding of triangle inequality is what I'm struggling with. So my understanding of triangle equality is that when the approximation ratio is 2, then the triangle inequality is satisfied. Is that correct?
Oh no. That is
Okay.
not a sufficient condition. That's
Okay.
just the triangle inequality is now the approximation ratio is implied from triangle inequality, not the other way.
Okay, thank you. That was what I was struggling with, but now I understand. Thank you.
Right. Okay. All righty. Okay, let's go back to this slide. So what we just explained is just this a few lines of writing, but the reasoning behind this is what I just show you on the whiteboard. Okay, so when we talk about greedy algorithm, we also talk about set cover, right? So you probably can go back to the slides on greedy algorithm. So we mentioned set cover. So set cover there. Once again, you have a collection. So the input here is that you have a collection of sets. You have a collection of subsets of a set. So that means you have a set first and a collection of subsets of the set. So a set, okay. Say you have n items and a collection of subsets of S. And then what we want to know is the output. Okay. A collection, or maybe a subcollection with the smallest cardinality, such that when you union the elements in it, it's equal to S. Okay, so let me write that one up. A subcollection so we call this C here, a subcollection C prime with the smallest cardinality, or that means that with the smallest number of subsets, with the smallest number of subsets, meaning smallest cardinality, such that when you union the elements, so on this elements, let's call it, don't use S, let's use S prime in C prime, then it's equal to S. Okay, so this problem is NP hard. Okay, so because it is a optimization problem, so what is the, when we say it's NP complete, obviously we are looking at its decision version. So decision version would be you have a set of S, you have a collection, and then you have a number K. So what you want to know here is that, can you have a subcollection C prime? So it's decision, right? Can you have, so this is that. There is a subcollection with C prime with the number of item subsets in C prime is less than or equal to K, such that you union them up is equal to S. So this is a decision version, and this is NP complete. Hence the optimization problem. Sometimes we also call it a search problem because you are searching for a solution. A search problem is NP hard. And there we talk about an approximation algorithm, and also we show the approximation ratio. We get a log big O of log n approximation ratio instead of a constant approximation ratio. So I would like you to, if you're interested, right? So, because obviously we are not going to revisit that problem here, but you may want to revisit that slides yourself. So with this, I am going to wrap up the topic of approximation algorithm. Again, we just have a brief introduction to this topic without going much, without going through a lot of techniques that have been developed. So so this is actually should be a course by itself. So every now and then I offered a graduate course at 700 level on approximation algorithms. So that, of course, we can talk about many different designing techniques and analysis techniques for coming up, for designing approximation algorithms to tackle NP-hard problems. For instance, one of the common technique is also called rounding technique. So you come up with a integral so ILP, so integral linear programming for solving a problem. But we know that that problem is NP-hard. And so one way to come up with a base to begin with is to change the integral requirement. So your solution can be real numbers. So that's a LP problem. Then we know how to solve this LP problem in polynomial time using simplex algorithm, for instance, or some other algorithms. But then your solution is a real number. Okay, so all your variables would have real values instead of integral values. So then this time we have to round them up. Okay, so we need to round real values to integers to come up with a solution to the problem we are having. So that is called a rounding technique. So that is one of the common technique we use, and sometimes we can prove a good approximation ratio. Sometimes we cannot. Then we have to use numerical analysis by running experiments to compare the results. Okay, so as I said, this is a brief introduction. We just don't have time to go through more. So next, we're going to look at another very useful algorithm analysis technique called amortized analysis. So that has to do with a sequence of operations on a given data structure. Okay, so now we are coming back to data structures now. So let's first open up that slides first. Okay. Oh, I lost you, looks like. Okay. I lost you. All right. We're back. Oh, by the way, how's your project going? Going okay?
Yeah, my partner and I have been slowly chipping away, making
Okay,
decent progress.
right. So,
Yeah.
so you know that you need to make a presentation, right, in December.
Yeah, we want to working on it, but not getting as far as long through it as I would like.
Okay, so of course you still have some time. Yeah, probably you are going to have a busy Thanksgiving break after your. Well, we can't have any big family gathering anyway, right? So you have time. Okay, anyway, so now let's look at amortized analysis. Okay, so once again, as I said, so we are now dealing, we're back to deal with data structures. So for instance, you have a stack, you have a queue, and the most complicated data structure is probably dynamic tables. So a table can expand and can shrink depending on the occupancy of the data. So you begin with a small table and you have more items to insert. So then I make a table larger. And then when you delete items out of it after a while, then I see the occupancy rate is low, then I can shrink my table. So that's called a dynamic table. So during this insertion deletion, you have a sequence of such operations. Then, of course, we want to know the cost of these operations. So for a single operation, the cost may be big, but if you look at a sequence of such costs, then a lot of this cost is just constant time. Okay, so for instance, if you have a stack operation, you can pop multiple elements out, right? So that multiple elements, when you pop it up, of course, you can only do one at a time. So that looks like a linear operation. But then in order to accumulate these items for you to pop multiple items, you have to have a push, several pushes, right? Several push operations before you reach this end. So you average them out, then you still get a constant time operation on average. So this analysis, by looking at a sequence of operation and average the cost of these sequence of operations, is called amortized analysis. And there are 3 techniques that we are going to talk about. Okay. All right, so I already mentioned the idea. So these are 3 techniques. One is the aggregate method. So what it means that we just sum them all up, and then take the average. So that's called aggregate, or accounting. So accounting means that for certain operation, I'm going to charge more, right? So I charge more, so then this extra charge will be used for some other operations. So that way we can also do an analysis. So that's called accounting method. And the most powerful one is called potential method. So we are going to give data structure potential energy. So you think of a data structure is a living organism that it has energy, right? So then we just use a function to measure what is in that data structure at that particular moment. So we're going to go through these methods, and finally we're going to look at dynamic tables. As I said, dynamic tables are probably the most complicated data structure operations. Okay, so aggregate analysis. So this is the most intuitive form of amortized analysis. Okay, so you have a sequence of n operations, And you just add the total time up. So that is T of n in total, and you have n operations. So you take the average. So that's T of n over n. So that is the average time per operation. Okay, so now let's look at 2 examples to explain this idea. So one is the stack operations I mentioned earlier. So let's say we have push and pop operations. And of course, you know, the operation of push and pop is a constant time. So if you have an n operation, you have a sequence of n operations of push and pops, then of course the worst time is still t. You sum them up, right? So that is linear, and then you divide it by n, so that it's constant time. So this is straightforward for this. But if you add a multi-pop, this is more interesting, right? So we can pop more than one item off in one operation. So let S denote a stack, and bar S bar be its size. Then we have now 3 operations: push, pop, and multi-pop. So multi-pop takes an argument k, which is the number of items to pop, and executes the pop operation on the stack k times. Okay, so that looks like this is a linear time operation for multi-pop. But however, as I said, in order to accumulate enough items for you to use multi-pop, you have to have several pushes beforehand. Okay, so then you average them up, you add them up, average them up, it's still a constant time. Okay, so so this is, well, this basically is just what I said. In order to have enough items to do a multi-pop, you have to have number of pushes beforehand. Okay, so you can imagine that if you just, so in other words, this multi-pop cannot happen frequently, right? It can only happen only when you have enough items accumulated in your stack. Okay, so then you add them up, and then you just like so that will be the at most twice of the number of pushes you do, right? So then it's still linear. You add them up, still linear, and divide it by n, then you still get a constant time. Next, we do a binary counter. So a counter just increment is an increment operation by 1 each time. So that's a counter. And let's say a binary counter. So this is just a pseudocode. So you each time you just increase it by 1. Okay, so then what is the, so let's look at this, all right? So let's say we set the array. So its counter is, let's say, A bit or K bit, right? So initially we start with all zeros. And then we want to find out the runtime of executing n increments, okay? So the way to increment this is that you have this addition operation that have carry bits, right? Okay, so the observation we have here is that when we increment I plus 1, then we will have a number of bits to flip, but not every bit flips every time. So for instance, this is an example. So we begin with 0, 0, 0. And then we add 1. So that's a flip 1 bit. So this is initial. And add 1, we flip 1 bit. So this 0 is flipped to 1. So we keep adding 1. And then this time, this 1 also flips. And then this 0 flips. Okay, and then we add 1 again. So this time, we only flips 1 bit. Okay, so this means that when we're here, we are going to flip 3 bits. After that, we flip 1 bit again, right? So that means that if you just look at one operation, so the number of bit flips, for instance, for this, it looks like linear, but this doesn't happen that many times. Doesn't happen often. So when you add them up, this is what we are having. Okay, so let's say we just look at the number of bit flips when you do the increment. Okay, so in a sequence of n operation, A1. Okay, so we start. So A1 is here. That's A1. And let's say you have an n bit. Okay. So A1 happens every time. Right? So A1 flips every operations. And then A2 flips every other operations, right? Because so for instance, the next time I start from 0, the next time I do is just 1. But then after that, so every other ones, and then I'm going to flip this bit to 1. So then you add 1 again. I just flip this 1 to 0, and flip that to yeah, so that you don't flip. Then every other one, then this bit will be flips. So then this bit will be every 3 times, right? I'm sorry, every 4 times. And then this will be every 8 times will be flipped, and then this will be every 16 times. So that's how we add them up. So so the total number of times of bit flips is this. So you just add them up. Okay, so then we take a floor to get integers. So this is n over 2 to the I minus 1. Oh, I'm sorry. This is k bits and n operations. So this n operations on a counter of k bit. Okay, so that's how I'm going to add this one up. So then this is less than or equal to n over 2 to the I. You take the n out, you sum this one up. Okay, so that's equal to 2. Okay, so you let this k go to infinity, because k is small, but then you make it bigger. Of course, this is less than or equal to. So that's 2n. With 2n is upper bound, so you divide it by n, so you still get a constant operation for constant time for each operation. So that is the simple aggregate method. You sum cost of n operations up and then divide it by n, take the average, in other words. Okay, so this is not really that interesting, right? Everybody knows how to do it. So the next one is accounting method. So that is somewhat interesting because you can overcharge certain operations, and the extra charge can be then used for some other operations. And that is accounting method. Okay. So we assign, now let's just look at the slides here. So we assign every operation and amortize cost in credits. So overcharge something, right? This may be more than or less than, or sometimes it could be less than the actual cost. And we put an overage in a piggy bank, the extra charge in the piggy bank, and we use that extra charge. This charge could be a positive and a negative to other, or you can think of it to supplement the cost of other operations. So, because if we don't have enough credits from the amortized cost to cover the actual cost of the operation, we have a deficit. So to cover the deficit, we extract the required credits from the piggy bank. Okay, so now let's see some example. Again, we use a stack and binary counters as example. So, so we have 3 operations for stack, for this stack. So we have push, pop, and multi-pop. So the actual cost for each of these operations is 1 for push, right? You just push one item. 1 for pop, and the smallest of k and the size of the stack is multi-pop. So that's the actual cost. So remember, we said earlier, in order to have a multi-pop, to have enough items in your stack, you should have enough pushes. And also, the pop, when you can pop something off, you must also have a push. So that means that I can overcharge a push by 1 unit. Right, so the actual cost of push is 1, then I add 1 unit. So that actual 1 unit is for pop. It doesn't matter a single pop or the multi-pop you would use, because that extra cost will be able to cover them. So hence the amortized cost would be I'd assign 2 to push, overcharge 1 unit for push, and 0 for pop and multi-pop for 0. So then this makes it easy because now I don't care what it is in the sequence of operations on stacks. I just look at the pushes. Each push has 2 units. Then of course you can only have at most linear, at most n many pushes. So that's at most 2 times n divided by n is still a constant time per operation. Okay, so this is interesting in this regard. So now let's look at binary counter. So we have an increment operation. So we set 2 sub-operations for increment. Okay, so just I plus 1. So we have 2 sub-operations. So one is simply to set the bit, which means that we set it to 1. So the actual cost of this operation is just 1. Okay, so we set it to 1, the actual cost is 1. And the other one is a clear a bit. So that means we set bit I to 0. The actual cost is also 1. Now, I want to overcharge something and then charge 0 for some other things. So what would be an amortized cost? So then each time the set operation, when you set it to 1, you imagine that it will be set to 0 later. Okay, so that means I can overcharge this operation by extra unit. So that extra unit is used for clearing it up later. So that means that I'm going to charge 2 for setting a bit and charge nothing for clearing a bit, because I can use extra credit from the piggy bank. You have to set it to 1 first before you can clear it, right? So then you just need to look at, for the sequence of n operation, you just count how many bits has been set to 1. Then I'm going to just add them up and then divide it by. So that is also a constant time operations on average. Okay. All right, so now next we're going to look at the most powerful method, which is called potential function or potential method. So we are going to look at a data structure as a whole. In other words, we are going to see it as a living organism that it can grow, it can shrink, it can change its status. So then we assign a measure, we call it potential energy, to a given state of the data structure. For instance, it may count the number of items or look at the occupancy rate, right? So every operation puts the data structure into a different state that either increases or decreases the potential energy. Okay, it's just a measure. Well, you know, in physics, people like to use energy to describe living things or things that change status, right? So they like to use energy. So we denote by DI the state of a data structure after the ith operation. Okay, so you have operation 1, 2, let's say you have n operation on a data structure D. And then after the ith operation, so that means you have O1, O2, OI, then you get at that moment DI. So at that moment, that's what the data structure looks like. And OI plus 1 will change DI to DI plus 1. Okay, so that's what we have shown. So now we are going to use a function. Okay, we call it capital phi, right? So this is a standard usage of notation, right? So in physics, people like to use this for energy. So we denote by capital phi of DI the potential energy of the data structure for DI. Okay, so which could be any function, but it has to satisfy some conditions. First, it is a real value function, and if you look at the following operation, so we denote the amortized cost of the ith operation by Ci hat. Okay, then Ci hat. So formally, this amortized cost is defined as the actual cost plus the change of the status. Okay, so or plus the change of the energy. So maybe that's easier to look at that way. So Ci hat is the amortized cost, not the real cost. Ci is the real cost, and this is the change of energy. Okay, from DI minus 1 to DI. So That's what this amortized cost is. So now we want, okay, so now this is some condition we want to have for any potential function. So now let's just add all the amortized costs up. Okay, so which is then we can derive what the conditions we need to meet. So by definition, then it is the actual cost plus the change of energy from di minus 1 to di. Okay, so you roll them up, the intermediate things repeat, right? So this is di minus 1. The next term will be di plus 1 minus di, so that di is canceled. So after you roll them up, you only have the beginning two status, the energy left, right? So the beginning energy and the ending energy. So that's what you have. Intermediate energies, they cancel each other. So maybe that's also why it's called energy function. So we just, what you get from the beginning and what you get at the end. So that's what you observed. In the middle, they cancel each other when you add them up. So that means it's the actual cost plus the energy change from the initial status to the ending status. Okay, so then if the ending energy is greater than or equal to the initial energy, then we know that the amortized cost is an upper bound of the actual cost. So this is good because this means that if this is greater than, if this is greater than or equal to 0, then the whole thing is greater than or equal to this. So that means because the actual cost is what I want to do, but it may not be so easy. Now, with the help of a potential function, then I can just compute this. That may become easy. So then it gives a upper bound. Now, if this upper bound is small enough, let's say if I take the average of this amortized cost is a constant, then I know the actual cost on average, it will have to be constant. So that is the condition for this potential function needs to meet. That is that the energy must be greater than or equal to, the ending energy must be greater than or equal to the initial energy. Okay, so that's what this requirement is. However, in practice, we normally have for any intermediate energy, it is also true, right? So not just for the ending one. So this guarantees we store up enough energy in advance. And traditionally, the initial energy, we can simply set it to 0. Okay, so to begin with, we don't have any energy. All right, so that is the energy function. So once again, any function will do. Now, this is any real value function will do. So phi could be just any function, as long as the initial energy is smaller than or equal to the ending energy. So that's the only requirement we need to make for this amortized analysis to go through. Because if this is true, then you look at the total cost of the amortized, the total amortized cost is greater than or equal to the actual cost. And that's what we want to know. And if this, after you divide it by n, is constant, then of course this will have to be, on average, will have to be constant, right? So the actual cost. So that is the idea of using energy function. Now, So why this is good? Because as we said, this is any function as long as this is satisfied. So which means that in your application, you just need to come up with a function that is easy to work with. Okay. All right. So there are a wide range of potential functions that can be used for the analysis. Okay, so once again, what we really want is the ending energy is at least the beginning energy. So now let's look at let's look at this stack. Let's use stack as an example to look at a simple potential function. So naturally at the beginning, your stack is empty, so it has no energy. Okay, so that's phi of D0, D0. Okay, so then at every moment in this n operations, okay, so your energy will be at least, so your stack cannot become negative. It could be 0, but it cannot become negative. I don't know how to say it, right? So negative energy. There isn't a negative energy. It has to be at least, it could be 0, but it could have more items. So that means that phi of di is always greater than or equal to 0. So that means that this is always true because at the beginning it's 0. So that's hence we can just use the number of items to indicate the energy of a stack. Okay, so now we compute the amortized cost. So the actual cost for push, the actual cost CI is 1, the push is 1. The change in potential is a difference of 1 because you push it, so we use a number of items in the stack as its energy, so that the difference then is 1. So the amortized cost for push then it is equal to 2. So 1 plus the actual cost then is 2. Then we can also prove that, we can also show that the multi-pop has amortized cost 0 because the actual cost is the minimum of the size of the stack, the current numbers in the stack, and k, because k is the parameter for the multi-pop operation. And the change in potential is a difference of this, right? So that means that so I have, you look at this potential. Okay, so the current moment is you begin with S, the size of S, and then after you do a multi-pop, so then you get what's remain, right? So what's remain is this, and this is S is this. Okay, so this is a new energy. So you do this, then what you are getting is this. The actual cost is this, so you add them up, that becomes 0. So likewise for pop, the actual cost is 1. The difference is -1 because you begin with S, and then you pop 1 off, you subtract 1. So this is the new energy. So new energy minus the previous energy, that becomes -1. So -1 adds 1. That then is 0. Okay, so then as you can see here, after you use potential function, you look at a sequence of operations, and then you just look at, so you just add each of these up, because all these pops are 0. So what you are getting is just a push is 2 units. right? So so this is a linear time for each operation in an AND operation sequence. So that is convenient. Okay, now we look at the counter, binary counter. Let's see what the potential function we can use. So again, it's always natural to look at the number of ones, right? In the counter after operation I, okay, because the number of bits is always fixed, but the number of ones is changed. Or you can use a number of zeros, but we can, because you start from number of zeros at the beginning, you want the energy to be 1. So that means that when when a bit is flipped from 0 to 1, then you gain energy. Okay, so then we just count the number of ones in the counter. That's the energy. So initially it's 0 because you start with all zeros. So then we let T sub I be the number of clear bits. So that after operation I. So this means that the actual cost CI is TI plus 1. So since we have to set 1 bit, okay, so you I plus 1, you at least we have to set 1 bit. You need to set 1 bit, and then the actual cost you have this. You clear up this many, so the actual cost is TI plus 1. Okay, so denote by BI the number of ones after the I's increment operation. So now we can see here is that if BI is 0, all bits were cleared. That implies that B sub I minus 1 is equal to TI, which is equal to K, meaning only when the binary counter was full can this happen. And BI is equal to BI minus 1 sub minus 1 minus TI, which is 0. When BI is greater than 1, now the number of ones after the I's operation, then that means that I will be from the number of ones earlier minus the number of bits that's clear, because you during this operation you clear this many bits and you need to set 1 bit up. Okay, so that's BI is equal to this. So then we look at this potential function. Then we look at the difference from the previous status, the energy, and to the current energy. So we get phi of di is equal to this, and the previous one is a b sub I minus 1. So that then is equal to 1 minus ti. Oops, my time is up. So let me just finish these 2 lines. So then the amortized cost of increment is the actual cost, that's Ti plus 1, plus the energy change. So that's 1 minus Ti, that's equal to 2. Okay, so, and then we can compute the amortized cost of, well, this is enough, right? Because you always do the increment. Okay, so that's 2. That's enough. All right. Okay, so then we are going to look at dynamic tables next Monday. Oh, by the way, we don't meet next Wednesday. You know that, right?
Yes.
Yeah, okay. So we have a 3-day Thanksgiving vacation. So you can use Wednesday, Friday for your project. All right, any question for me?
Not at this time.
Okay,
So,
all right.
so for the project, we are gonna just directly present in December. Like, are we gonna have a checkpoint or anything before that with you?
No, so I don't need to do any checkpoints. So you make a presentation, then I may I could make some suggestion during your presentation. Then you still have 1 week of time to fix it or to improve it.
Okay,
Do-
thank you.
Thanks.
Yeah. Okay. So see you next Monday.
Thank you.
Bye-bye.